Hi, we're Team Perry from Israel. My name is Idan and I'm in charge of the software of the robot.
My name is Shani and I'm also in charge of the software.
My name is Lihi and I'm in charge of the mechanics and structure of the robots as well as the design and the set.
My name is Dor and I'm responsible for the electromechanics of the robot as well as the set of the show. Let us begin with the voltage and control card. We handcrafted and designed this card in a school lab. We started with adding a switch that enables the voltage to flow through the system. We then added a push button that is connected to the ESP controller and allows us to start our code. In order to provide safety to our system in case of short circuit, we connected a fuse that will burn to prevent destruction of other components. In addition, we added a LED that let us know when the system operates, a diode that makes sure the flow of the voltage goes to the right direction, and a resistor. Lastly, we added several terminal blocks connectors that connects the card directly to the ESP, the motor driver, and the power stabilizer.
The motor driver's purpose is to control the speed and direction of the motors, who move the omniwheels of the robots. This driver also allows us to send a higher voltage to each of the motors. In each robot, we have one motor driver for the two DC motors that are placed on the right and left sides of the robots. We chose to use these motors, DC and not a different kind, because it works in a direct current and works on batteries, which is great for our mobility.
The power stabilizer is a component which receives power from the batteries and reduces it to the power needed in order to drive the motors. It is connected from the voltage and control card to the motor driver. We use 11.1 volt battery in each of our robots. That is the power needed for moving our robots.
Adding a variety of sensors caused a shortage of 5-volt ports in our robots. We added handcrafted voltage and ground extensions, which we attached to the top of each of the robots and wired straight to the ESP, so we now have more than enough usable 5-volt ports.
The ESP32 board is a versatile microcontroller development board that offers advanced features and capabilities such as Bluetooth connectivity and a dual-core processor. The ESP32 is capable of executing code faster than a standard Arduino board like an Arduino Uno or Mega. It is very useful to us because we need our robots to make fast calculations. We use the Bluetooth feature to make sure our robots are connected and start the performance at the same time. We have also used this feature consistently throughout our development of the robots to check the robot sensors during the performance, and we'll get to why it was problematic shortly. The MPU 6050 sensor is an inertial measurement unit. It combines a 3-axis gyroscope and a 3-axis accelerometer to measure linear acceleration and angular velocity. We use the gyroscope in the MPU 6050 for angle measurements. The gyroscope contains a set of 4 masses. When an angular motion is applied, there is a change in capacitance between the masses depending on the axis of the angular movement. This change in capacitance is sensed and then converted into a reading. When we thought about our performance, we originally wanted to try and build race cars for a Mario Kart project. Unfortunately, we were not able to use the project idea, but we still toyed with the idea of navigating robots. So in the end, we settled on tiny robots that will be able to be fast and precise using the MPU 6050 as a crucial navigation tool.
In our robots, we use ultrasonic GYUS42V2, which is a sensor that measures distance. The ultrasonic sends out sound waves and measures the time until they bounce off the surface and back to it. Using the speed of sound and the measured time, the ultrasonic calculates the distance. In our performance, we use the ultrasonic as part of our error prevention system to detect obstacles in front of our robot and stop before it collides with them. We also use the QTR8, which is a line sensor, but we use it because of its ability to differentiate between black and white surfaces. The sensor uses infrared LEDs and phototransistors to measure the reflectance of the surfaces. White surfaces reflect a lot of infrared light, in contrast to black surfaces that reflect very little of it. Like the ultrasonic, we use the QTR8 in our error prevention system to detect when our robot is about to cross the border and prevent it. So, why did we choose these 4 features? Well, we chose the ESP32 because it is a very powerful processor and it has Bluetooth capabilities that allows us to see the output of our sensors and test our robot in real time without having to bring the entire computer with us. We chose the gyro because we wanted to create a show with complex movement, and for a show like this we had to know about our location and angle at all time, and the gyro allows us to do that. We chose the QTR8, which is the infrared sensor, because during the national competition our robot crossed the border and we lost a lot of points because of that. We wanted to make sure it won't happen this time, so we added it in order to make sure the robot can correct itself when it is going out of bounds. We added the ultrasonic because during the national competition a robot smashed into our scenery, and we wanted to make sure it won't happen again. Now with the ultrasonic, the robot can stop itself before it hits the scenery. We wanted to create robots that can perform complex movement all around the stage. We also wanted our movement to be flexible, and so we could change the show and suit it to our needs. And we certainly did that. We created a system based on vectors. We tell our robots at what angle to move, how much to move, and at what speed to move. And they do that. At first, the robot rotates that exact angle using the gyro. The robot knows thanks to the gyro sensor, and even if it's a little off, the robot knows to correct itself. It rotates again until it gets it right. After the robot finished rotating to that exact angle, it starts moving. The robot calculates how much time it needs to move because it knows it's his speed in meters per second because we measured it, and also it knows the distance it has to travel, so it calculates the time. And during the walk, the robot still calculates his angle every 10 milliseconds, and once the robot sees that it's a little off, it knows to correct itself. It reduces the speed of one of the wheels and rotates during the walk just a little bit to correct itself. That's how it knows to move straight and not to diverge from its path. During the development of our robots, we encountered several challenges. One time, the left motor in all of the robots stopped working, and we had no idea why. We tried switching up the ESP, switching up the motor, checking the connections, but the problem still remained. We asked our mentor about it, and he brought in a device called oscilloscope. And with that device, you can see you can see what happened in the circuit, and we traced the problem, and we saw that the motor driver did not get any voltage from the ESP. So we checked why the ESP wasn't sending out any voltage, and we discovered that there was a problem in the code. We used a really simple motor code to find out, to test the motors, but the thing is, we never thought about checking the code itself, and that's where the problem was, and it took us a lot of time to fix it. Ever since that day, we started using the filter system. The filter system said that when you encounter a problem, you write down all the possible causes for that problem and eliminate and test all the causes.
As I mentioned previously, the Bluetooth feature was useful until a specific point, but then it was only cause of trouble. For a long time in our development of the robots, we were certain that an error in our calculations with the MPU 6050 was caused because of something called a driver drift. This drift is supposedly caused by faulty hardware and or uncontrollable noise. For this reason, we tried to figure out a solution for this problem. It took us some time to figure out the problem wasn't caused by a drift, but because of Bluetooth signals we constantly sent to our devices. Since the Bluetooth signal takes time to send, it interrupted the MPU's calculations. So in the end, we no longer use it for testing and simply let the robots perform without constantly seeing their MPU readings.
The set consists of 3 PVC panels. Each of them has its own weakness. All 3 are equipped with a 7.2 volt battery, an Arduino Uno, and at least one servo motor.
The first 2 panels are created to look like a gate, and the left one is equipped with an ultrasonic so that when the agent starts moving and moves further away from the ultrasonic, the gates open. On the second panel, we can see a servo moving left to right, and on the last one, we can see the camera attached to the servo. It is the same on the second panel. It was only for the show. And on the other side of the panel, we have the computer Agent Perry needs to get to and supposedly use to get the information he needs.